Okay, so today we're going to be looking at how using chi-squared statistical test can be used to analyze Mendel's actual experimental results. So chi-squared is a statistical test that is commonly used to compare observed data with the data we expect to obtain according to a specific hypothesis. Though interestingly, this is not a normal hypothesis that many of you have used in basic science classes. This is called a null hypothesis, which states that there is no significant difference between the expected and the observed results. So, here we go. Let's look at Mendel's experiment. You get a nice little, before we move on, let me just grab my pen. Blue pen. So here we can see that's the chi-squared equation. It's actually quite simple. And for those of you not familiar with, that means sum of. So Mendel did many experiments where he collected lots and lots of data, and he did a dihybrid cross, many dihybrid crosses, but we're going to look at one particular one, where he fertilized the seeds that appeared round and yellow with like seeds, and he raised from there, and he got a total of 556 seeds produced from 15 plants, and these were his results. But before we get to that, let's just look at the basic experiment. So we're looking over here at this experiment. We'll talk about the other one later. So he started off with the parental generation, and he started off with true breeding round yellow peas crossed with true breeding wrinkled green peas. And so the true breeding or homozygous round yellow pea plant could only produce gametes, egg and sperm, that would have big R and big R and big Y, because that's all they had. And the homozygous recessive parent over here could only pass on little r's and little y's. So that's the only gametes they could produce. So obviously the F1 generation would get one big R, one little r, one big Y, one little y. And so all of the F1 generation were heterozygous. But they appeared with the dominant phenotypes in their, so yellow and round. But when you allow this heterozygous big R, big Y, little y plant to breed, he hypothesized that independent assortment would occur, that the big R factor could go with the big Y factor, or the big R factor could go with the little Y factor. The little R factor, let me just erase so we can not get too confusing. The little R factor could go with the big Y, or the little r could go with the little y. And so we see here the four combinations that are possible, okay, for the gametes. Again, these are the gametes, and notice here that this figure does it opposite of the way I do it. It put the sperm on the top of the punnett square and the eggs on the side. I usually do it vice versa. It doesn't really matter, except for it's just much easier if you are consistent. And I'm going to choose a different color. Let's go with purple. Okay, so here we see, again, the exact same possibilities because both parents have the exact same genetics. So when you go through, you can see fertilization. And so here, this individual, big R, big Y, big Y. That gamete fertilized by that gamete, which gives us a round yellow seed. Now, we're not going to pay too much attention to genotype ratios. We care more about phenotype ratios right now. So here we see one round yellow, 2, 3, 4, 5, 6, 7, 8, 9. So 9 out of 16 offspring, 9/16, are round and yellow, have both dominant phenotypes. Then, if we look carefully, we can see, oh, if that gamete is fertilized by that gamete, you get a wrinkled yellow, which is like neither parent, which was round and yellow. It still has the dominant round phenotype, but it is now wrinkled here, whereas the parent was round. So the wrinkled trait skipped a generation from the P generation, which was the green wrinkled parent. Now, how many wrinkled yellow peas can we get in this? 1, 2, 3. or 3/16. And then we see we've got another combination. So let's look at this gamete right here, big R, little y, being fertilized by big R, little y. And so now we get another unique phenotype combination, having the round dominant phenotype like, again, its parent. But, again, now the green has skipped a generation and come from the parental generation, been passed down through. And so now we have a round green pea. And how many of those do we have? We have 1, 2, 3. 3/16 of them. And then if we take a look at 1, so we have little r, little y gamete being fertilized by little r, little y gamete to make a possible little r, little y offspring. The chances of that happening are 1 in 16. So those are the probabilities, the expected probabilities, if we have independent assortment. So, independent assortment. Oh, where did my pen go? Independent assortment. Now, when Mendel did his experiment, he had 556 offspring produced when he bred round yellow plants with another round yellow plant, but he knew it was the hybrid, big Y, big R, big Y, little y, crossed with big R, big Y, little y. Okay. But he didn't know, did the big R's and big Y's have to stay together? Did the little R, little y's have to stay together? If so, the only offspring you would produce would be round yellow or wrinkled green, and no new combinations like this wrinkled yellow or this round green. So he hypothesized two different hypotheses. Dependent assortment, where genes, round and yellow, have to stay together, and genes for green and wrinkled have to stay together. But when he did his experiment, as we can see here, he got wrinkled yellow and he got round green, which were new combinations. So we can automatically discount that. That hypothesis is rejected by the simple observation that he grew 101 wrinkled yellow and 108 round green peas, which would not be possible if round and yellow had to stick together and if wrinkled and green alleles had to stick together. So now we have to see whether he's on the right track with his independent assortment hypothesis. Now, of course, if you studied meiosis, we know he was on the right track, but we're going to look at the statistical analysis of this. So back to our 556 offspring, 315 round and yellow, 101 wrinkled and yellow, 108 round and green, and 32 wrinkled and green. Now, what would Mendel expect if he was growing 556 offspring, according to this hypothesis of independent assortment? 9/16 of them should be round and yellow. Now, if you do the math on that, 9/16 of 556 is 312.75. I know you can't get 0.75 of a pea, but we don't want to round at this point. It will mess up our math analysis later. And then how many should be green and round? Well, 3/16. So 3/16 of 556 is 104.25. And again, 3/16 for the wrinkled yellow. So 104.25. And 1/16 of the double recessive would be 34.75. And just checking our math, yes, if we did our math correctly, our total should be 556. So in chi-squared statistical tests, we are testing the null hypothesis that there is no significant difference between the expected results, which are over here, and this is based on the punnett square, though ours was a dihybrid, so I'll draw 16 squares. That was testing independent assortment, predicted by Mendel's principle of segregation and Mendel's principle of independent assortment. So there's no difference between the expected results predicted and, oh, I forgot that, and the observed results. Here we have his observed results, how many he actually grew. And we know this totals up to 556. We know this totals up to 556. Okay, now you might just look at that table and go, well, of course, 315 is not equal to 312.75. 101 is not equal to 104.25. Not equal, not equal. But that's too simple. We would never expect everything to perfectly happen during random fertilization. You would never expect a family to have, with 2 children, to always have 1 boy and 1 girl. There's a possibility of having 2 boys. There's a possibility of having 2 girls. Though if you get a large enough population, maybe a population of 1,000 pregnancies, you would expect approximately 500 girls and approximately 500 boys. You wouldn't be surprised if it was a little bit over for one and a little bit under for the other. But how much is 2 over? How much is 2 under? How much is close enough? That's what chi-squared lets us get to. So this is a biology lecture, not a statistics lecture. So I'm just showing you how to use the chi-squared statistical test. I am not going to go into how it was derived in the first place. I'm sure if you looked on other videos, you could find that from other people. So we need to determine the relative standard to serve as the basis for accepting or rejecting this hypothesis. So, is 315 close enough to 312.75, or is it not close enough? Is 101 close enough or not close enough to 104.25, etc., etc. The relative standard used in biological research is right here. There are multiple choices you can make. Different studies use different acceptance values, but we use the 0.05 value. The p-value is the probability that the deviation of the observed from the expected is due to chance alone. Let me say that again. Due to chance alone, with no other forces that are acting. Okay. What does it mean by the 0.05? You would expect any deviation to be due from chance alone 5% of the time or less. And in biology, we say 5% of the time or less, that's good enough. There are other subject areas of study that may say, no, it needs to be 1% of the time or less. There are other subject areas that are like, we'll take a little bit more, so maybe 10% of the time or less. Okay, so that brings us to our chi-squared table. And our chi-squared table we will come back to, but here's a few things. We have degrees of freedom. Degrees of freedom, the calculation for that is n minus 1, where n are the number of phenotypes in genetics. Now we are looking at 4 phenotypes, so 4 minus 1. So that means the only thing we're going to care about in this, I'm going to change that color, it's driving me crazy. The only thing we care about is the 3 degrees of freedom. Okay. But we're in biology, so we only care about the 0.05 p-value, which means if we go down, this is our chi-squared value that we will compare our analysis against. So, if our chi-squared value that we calculate is less than 7.815 for this example, then there's insignificant deviation. We have no reason to doubt our null hypothesis, and our expected and our observed values are statistically equivalent. If the chi-squared value is greater than 7.815, or greater than or equal to 7.815, then we have reason to doubt our hypothesis. There's significant deviation, and the observed counts of the yellow smooth, the wrinkled yellow, the smooth green, and the wrinkled green do not match with our expected values based on our Punnett square that showed independent assortment. So let's look at how we do the math. So this is just a broken down version of that chi-squared equation. Again, remember the chi-squared equation is chi-squared equals the sum of the observed minus the expected squared, so that way positive and negatives won't cause any trouble, divided by the expected. Okay. Now, here are our observed values from Mendel's actual experiment. 315, 101, 108, 32 equals 556. So 556 times 9/16, because we expect 9/16 of the offspring to be round and yellow. So we just multiplied to find out what our expected, and that's how I got my original values. And that is 312.75. And 556 times 3/16, that's 101. Oh, sorry, 104. I can read 0.25. 556 times 3/16, and that is 104.25 again. So we expect that these should be equal. And 101 and 108, are they statistically equal? Are they not statistically equal in the sample size of 556? That's what we're going to help figure out. And then finally, 556 times 1/16, and that is 34.75. And if you total it up, we find it, yes, it does equal 556. So all is good. We know our observed from Mendel's experiment. We know our expected based on the Punnett squares and the sample size total. So now many of you could probably just throw this in an Excel document, but I'm going to work it out for you. So observed minus expected is, I'll work it out for one column and then I'm going to jump down to the very bottom column. And that would be, here we go, observed 315 minus expected 312.75. What does that equal? That equals 2.25. So if you take 2.25, now don't round ever, maintain everything in your calculator, squared, that is 5.0625. At some point I start rounding because I just run out of space. And so here we go, 2.25 squared divided by the expected, which was 312.75, that equals 0.0162. Okay, and really all we need is the to the thousandths place, because of the chi-square table only goes to 3 digits past the decimal. Okay, now I'm going to just skip these steps here. You could fill them in for yourself. You should know how to do that math. And I'll just set it up at this point. So the observed 101 minus the expected 104.25 squared divided by the expected 104.25. What does that equal? That equals 0.1013. And again, those are the only digits that really matter, but I'll keep it to the fourth, so just so you can see it. And then now, observed 108 minus expected 104.25 squared divided by expected 104.25. What does that equal? That equals 0.1349, which would be, if we kept it to 3 digits there, 0.135, but we'll just leave to the fourth right now. And then here we have 7 erase. So here we have our expected, observed of 32 minus our expected of 34.75 squared divided by our expected 34.75. That equals 0.2176. And again, here we go. You total it up. Now there might be some rounding in here, so your number might vary on the third digit, but don't worry. Is chi-squared total. So, come on, Hyler. This number plus this number plus this number plus this number gives us a total. That's a plus sign, plus, plus, equals 0.470. That's our chi-squared value. What does our chi-squared value mean? We have to go back up to our chi-squared table. Again, we're not going to explain how statisticians derive the chi-squared table. That's for a totally different discussion. We're going to talk about how biologists can use it. So we came up with a chi-squared value of 0. Our calculated chi-squared value is 0.470. 0.470 is definitely less than 7.815. Remember again, this spot right here. 3 degrees of freedom, where the p-value is 0.05. So we would expect any deviation to be due to chance alone 5% of the time or less. We're willing to put up with 5% of like, I don't know, but 95% of, probably. So that means we fall on this side. We have no reason to doubt our hypothesis that it is insignificant deviation. What does that mean? If we look at these statements, there is no reason to doubt the null hypothesis. The expected values, let's see if we can steal this table. Let's put on the arrow clip. Copy. Okay. The expected values listed above are statistically let's rephrase that. Do not statistically differ from the observed values counted in Mendel's garden experiment. And then it's 3 degrees of freedom, p to the 0.05. Okay, that was what we were using. So, yes, statistically speaking, 315 is equal to 312.75. 101 is equal to 104.25 statistically speaking. 108 is statistically speaking equal to 104.25. And 32 is statistically equal to 34.75 when you have a sample size of 556. So yes, going back to Mendel's actual hypothesis he was testing, yes, there was independent assortment between the round and wrinkled, yellow and green. The shape gene is independent of the seed color gene. Round can go with yellow, round can go with green, wrinkled can go with yellow, wrinkled can go with green. And so if you breed heterozygous offspring together, big R, big Y, little y, with itself, you would expect to find 9/16 with the double dominant, 3/16 with the one dominant, one recessive, 3/16 with recessive dominant, and 1/16 with the double recessive. And if you do this experiment and you do your chi-squared test, you will find this for yourself.